That's me. All right, so chapter 6, part 2 is our task today. So we're going to extend our study of matrices to multiplication, inverses, and determinants. Matrix, multiplication, inverse, and determinant. Making sure everything's going in. Yeah, looks like it. All right, so we're going to learn to multiply matrices and find determinants and use those determinants to find the inverses. First of all, definition, identity matrix. So this is a matrix of dimension n by n. So it's a square matrix. It's usually capital letter I. And again, it's always an n by n. So it is a square matrix. And it's such that it's all ones along the main diagonal and all zeros below. So you can extrapolate from that what the 4x4 and 5x5 and 2x2 and so on would look like. So I've written it as a 3x3, but that's what I had room for, because that's what I had room for. But it could be any dimension as long as it's square, as long as the rows and columns are equal. An inverse matrix. So think about how inverses work in multiplication. If I multiply 7 times 1 over 7, that equals 1, right? Because 1 is the multiplicative identity. In other words, whatever I multiply by 1, the result is that thing. 7 times 1 is 7. 42 times 1 is 42. That's why 1 is the multiplicative identity. The reason why this is the matrix multiplication identity is because whatever matrix I multiply by this, provided the dimensions match, the result will be that original matrix. So this is the identity matrix. So as a consequence, if I multiply a matrix by its inverse, which is indicated with this superscript -1, that's going to equal the corresponding identity matrix. So this inverse matrix is a matrix such that if I multiply it by the original matrix, the result is the identity matrix. This is only possible in square matrices. They also must have a non-zero determinant, but we'll get to that in a second. In fact, that's the next definition. Invertible means the inverse exists. And for the inverse to exist, this must be square and have a non-zero determinant. A singular matrix is one for which no inverse exists. And then that determinant, it's found by formula, and it's only possible to find these in square matrices. But the determinant is a number we use for formulas. So it allows us to know certain things about the matrix. The determinant, the formula for the determinant is different for every size matrix. So it's different for a 2x2 versus a 3x3 versus a 4x4. Each of those have their own and increasingly complex formulas for finding the determinant. Your calculator can find a determinant for any reasonably sized matrix. So beyond a 2x2, it's very easy to find it for a 2x2. It's one single line, one single expression. But if we have a 3x3, it's 3 separate, pretty complex expressions. 4x4, it increases by orders of magnitude. So beyond a 2x2 determinant, we'll find using the calculator exclusively. Okay, questions about this? All right. So matrix multiplication. The best way to explain this is through an example. Let's see. 2, 3. Okay, so let's do an example. So let's let A equal 1, 0, 2, 3, -2, 5. I'm just making up stuff off the top of my head. And B is going to equal 1, 2, 2, 1, 0, 3. So step 1 in matrix multiplication is determine if the product exists. And the way we do that is dimensional analysis. We analyze the dimensions. So rows by columns. What is the dimension of A, Anna? Excellent. And then what is the dimension of B, Elizabeth? 3 by 2. So in order for a product to be defined, the columns in the first factor must match the rows in the second. Those numbers have to be identical. So these two numbers have to match. In this case, they do, and so the product exists. If they don't match, the product does not exist. And so if it exists, we'll name it by using both of the variables together, and then it will take its rows from the first matrix and its columns from the second. So the product exists, and it will be a 2 by 2 matrix. So step 2 is going to be to run the matrix multiplication algorithm. So it's a step-by-step process, which I'll explain. Then we got save myself a little writing by copying this. So we're going to do A times B which is this times this, and it's going to equal AB, which is a 2 by 2, but I'm going to give myself a lot of room because each one of those elements is going to have a pretty complicated expression. So the algorithm to find the product is this. I take my rows from the first matrix and my columns from the second. So the row 1, column 1 in my product matrix is going to be the product of the first row and the first column. I'm going to multiply the corresponding elements and then add them all together. The first row, first column, I multiply the first row by the first column. So 1 times 1 plus 0 times 2 plus 2 times 0. And then I just repeat that process. Row 1, column 2 is going to be row 1 times column 2. So that's going to be 1 times 2, 0 times 1, plus 2 times 3. And then row 2, column 1 is row 2 times column 1. So 3 times 1 plus -2 times 2 plus 5 times 0. And then the last one, I hate that highlighter color. It is no good. Something interesting. Orange. Yeah, maybe that'll work. So row 2, column 2, row 2 times column 2. So that's 3 times 2 plus -2 times 1 plus 5 times 3. Like so. So that's the algorithm. This is the result. We, of course, have to simplify, but the job is basically done at this point. The potential for error really is only high in those first few steps. So 1 times 1 is 1, and then plus 0 is still 1. 1 times 2 is 2, plus 0 plus 6 is 8. And then 3 times 1 is 3, plus a negative 4 is negative 1, plus 0 is still negative 1. 3 times 2 is 6, plus negative 2 is 4, plus 15 is 19. So there's our product matrix. Now let's check ourselves by using the calculator. So in your calculator, and you really will want to practice this, because the reason why people do so well on this test is not that the material is so easy. It's that everything can be checked with a calculator quickly and efficiently. So all your answers, all you got to do is plug it in the calculator and you can check yourself. And of course, you can just find them in the first place, on the calculator if you wish. But not knowing how to use the calculator will be a huge handicap in this chapter. Huge handicap. So make sure you do so. We're going to start by defining the matrices. I'm going to go over to the Edit tab, hit Matrix, go over to Edit, and we'll edit A to match our A. This is a 2 rows by 3 columns. And it is 1, 0, 2, and 3, negative 2, 5. And then let's go back to Matrix, go back to Edit, and now we'll edit B as well. This is 3 rows by 2 columns. And it is 1, 2, 2, 1, 0, 3. So I'll put on this, and I'll do matrix A times matrix B. Get this result, and I see that it matches my answer, so we're good to go. So there's really no way you should miss these on the quiz or test. Shouldn't have. And yet I predict it will. Not for you guys so much. You guys did great on that chapter 5 test. Well, it's kind of feast or famine. I had A's and I had D's. Not a lot in between. That's okay though. That's really to be expected, because it's just not a subject material you're going to approach with a mediocre effort. You're either going to throw your hands up and pray to the gods of mathematics, or you're going to study your butt off and make it 100 like some of you did. Yeah, if you made even a 90 on that test, I'm spectacularly impressed. It was evidentiary of a great skill. And I was, humility aside, kind of pleasantly surprised at the efficiency of my teaching this semester, because we've got all these difficulties. And I thought, wow, man, I got an average of 80 plus on this extremely hard test. Made me feel good about myself. So anyway, this is an example that you saw me do. Here's one for you. Now be careful with your dimensional analysis. It's not the same as the previous problem. I want you to try to do this by hand, exactly the way you just saw me do it, and then check yourself and calculate it. Make sure and raise your hand and ask me if you get confused. A few minutes on this, try to get it done in that amount of time. One thing our modern educational approach lacks is a sense of urgency. And then we give you that ACT 60 questions in 60 minutes, and urgency is absolutely required. So not a bad thing to cultivate. So we've got, this is 3 by 2, 2 by 3. The product is defined, it will be a 3 by 2. Row, first element, first row, first column. It's 4 times 7 plus 1. Next one. This one. See if you can carry on from there. Figure out what to do. Keep pushing mathematics back, further back. I learned this when I was a sophomore in college. Get the first few right, you're probably going to get the rest of them right. Some more. So these two, the only thing we care about the inner box elements here is that they match. Oh, that's fine. Once we find they match, we disregard them. We've got A and D. So for each of the values, it would be the product of the row times the column. So 4, 5 is your first row, 7 is your first column, so your first element. Got one more column out there. I will do, yeah. It'd be 4 times 1 plus 5 times 4. And you've got 3 total rows, so be conscious of that. Once you get an answer, check yourself with the calculator. Also glance over at your neighbor's paper and see if you guys agree. If that's feasible. Some of you guys sadly lacking in neighbors today. Yes, ma'am. So with these once we have one is outermost values to final products. So it's going to be a 3 rows. It's 3 rows, not 3 columns. So what do you throw? So you got 4 times 7. Wait, that's 73.
Almost 1 times 1,
So
plus
that's
73. Almost at the same name.
So first one, 4 times 7 plus 5 times 2. So this row times this one. And the next one is going to be the first row again times the second. 4 times 5 times 6. Third row, see if you can carry on from there to the second and third row. Okay, so let's discuss this one. I know some of you guys are still working on it, but that's probably enough time spent on that one for now. First of all, Grayson, tell me what the dimension of our product matrix will be. Excellent. And that's different than the previous one by design. I wanted to challenge you guys and see if you can figure that out. So 3 by 3. And then, so there will be 9 total elements. Tell me what those elements are, Carson.
38, 30, 44, 25, 54, 73, negative 48, negative 18, and negative 30.
Negative what?
30.
That seems right to me. Can anybody confirm this? You got the same thing? Okay, then it's almost certainly correct. Interesting thing about matrices is they're really good at encoding data. And you see the complexity and the seeming randomness that occurs when you multiply 2 matrices together. It would be difficult for you to just take the one set of numbers, the other, and wind up with the matrix product without some cue as to what operation took place. Well, that's exactly why this was used to encode data by the Nazis in the form of the Enigma machine. So they created a little typewriter that you would put in matrix information and it would encode the data in a certain way. And then, another machine, you put in the same matrix, it would decode the data. So the United States could not crack it. And we were not doing well in World War II for the first couple of years. So 1941, 1942, we were not doing all that well. And then all of a sudden in 1943, the fates landed on the side of the Allies and things started going really well for us. There's a reason why. A man named Alan Turing, the first computer scientist, developed what's called the Turing machine, which was the first computer, secret, nobody knew about it, kept it in a hidden laboratory, and he had some British intelligence agents working for him. Now, Alan Turing was famously a homosexual, and he was gay in a time when it was not cool to be gay. It was not at all accepted. He had to keep it hidden. In fact, he had to keep it so hidden, he had to go on pretend dates with girls so that his peers would not question his sexuality. So he was on one of these pretend dates with a chick, and they're talking about these messages they send back and forth to each other on the Enigma machine, which they intercepted. They sent them to Turing, and Turing tried to decode them with his Turing machine unsuccessfully for those first few years. And Great Britain was in the war long before we were. So he was several years deep into this. They were about to pull the plug on him. He's on a fake date with a girl that he's not even remotely interested in. Probably checking out dudes in the bar, who knows. So anyway, the chick says, at the end of every message, they say something that's formatted similarly. I think it's Heil Hitler. And so Turing dropped his drink and ran out of the room immediately. Went back, put that data into his machine, and broke the code that night. So from that point forward, we knew everything the Nazis were going to do before they did it. And as a consequence, won the war. Now, they could not break the Americas code. You know what our code was? The Navajo language. So the American Navajo language, which only like 10 people spoke at this point, a handful of people still spoke it, and so nobody could crack it. It was uncrackable. But the Enigma, we got that bad boy thanks to Turing. And kind of a sad ending to that story. As a consequence of his being gay, he was charged with homosexuality and sentenced to chemical castration. So and that's where they inject you with something that keeps you from committing any deeds that would violate that, I guess. As a consequence, he went into a depression and ended up killing himself with a very interesting technique. He injected cyanide into an apple and took a big bite. So Alan Turing, the greatest computer scientist to ever live, the man that saved us from the Nazis, dead as a consequence of his sexual orientation. Pretty sad story. But the bite out of an apple is interesting because Steve Jobs and Wozniak knew that. So what company has a bite out of an apple for its logo? Apple. Yeah. That's an homage to Alan Turing. They're saying, we appreciate you, bro. We wouldn't have made you eat that out. So anyway, back to this. So we'll just use a calculator on this one. And going forward, I won't work them out by hand as a rule. I'll just use a calculator to save time because it is somewhat tedious to do so. But the power of matrices and coding data, pretty fascinating. Took a genius as great as Alan Turing to decode that data. If we go to matrices and edit A, this is a 3 rows by 2 columns. Oh, the same one?
Yeah.
Oh, we don't want to do that. There we go. We'll do this one. So this is a 2 rows by 3 columns. And it is 2, -1, 0, 3, 2, -1. And then we'll define B. And we want B to be 3 rows by 1 column. It is 4, 2, -1. -4, thank you, sir. We'll get it right. Okay, so in order to multiply these, I call matrix A times matrix B. And the answer is 2 by 1, -10 and -7. Remember that dimensional analysis. So we only care that these match, and once we confirm they match, we throw them away, and then the dimension of our product matrix will come from the leftover data, the outer of those dimensions originally. Okay, questions about this? Did you do it by hand if you had to?
Yeah.
Did you do it by calculator? So some properties of matrix multiplication, these are on page 377, so you don't have to write them down, but we will discuss them briefly because you're going to see me employ these. There is an associative property of a string of matrix factors. So I could do this product first and then multiply by this. I could do this product first and then multiply by that. However, you should probably make a mental note that matrix multiplication is not commutative. In other words, A times B does not necessarily equal B times A. So I can't reverse the order of the factors and get the same result. In fact, often if I reverse the orders, the product wouldn't even be defined. You know, that dimensional analysis would fail in some of those previous examples. So A times B is not as a rule equal to B times A. This is a primary thing you should remember, but it's something that's not on this list, so you may want to jot that down. The product of 2 matrices is not commutative. Not commutative. So let's talk about football. You guys watch the Cowboys game the other night? Pretty exciting. Really, I'm not as big of a Cowboy fan now that Whitten doesn't play for the team, but still one of my top 10 teams, let's say. So here we've got a list of scores for 3 teams. These are the top 3 teams in some imaginary conference. 27-7, 21-2, 24-12, 18-3, 21-14, 12, and 9. That was touchdowns, field goals, point after, and 2-point conversions, respectively, for those 3 teams. And we want to quickly and efficiently arrive at a total points for each of those 3 teams and determine which of those 3 teams scored the most points this season. Now, of course, I could go through and multiply these one at a time, add up the result, but more efficiently, I can create 2 matrices. You know what I can tell about this thing? Their kicker's not great. They don't trust that boy or something. Or they really have maybe a fullback that's going to get 3 yards every play or 4 yards every play, no matter what. But anyway, let's multiply this by this points matrix. So this is 6, 3, 1, 2. 6 points for a touchdown, 3 for a field goal, 1 for a point after, and 2 for a 2-point conversion. So this is 1, 2, 3 by 1, 2, 3, 4. And we're going to try to multiply that by 4 by 1. And you see these match. So we disconsider them, and we know our product is going to be sum 3 by 1. So that's going to have 3 elements total in one column. Let's use the calculator for this again, just to save ourselves some time. So we want this one to be a 3 by 4, and we want it to be 27 times 7 times 21 times 2. And this one's 24, 12, 18, 3, stop me if I make a boo-boo, 21, 14, 12, and 9. Double checking myself here. Looks good. Looks good. All right, and then we want to define B as a 4 by 1, and it's going to be 6, 3, 1, 2. So now if I've already called A times B for my previous input. If I hit second and enter, it just recalls that exact same thing. 208, 204, 198. The top row is highest, and so Tiger scored the most points total in this case. And that was a little bit quicker than going through and manually adding, multiplying, and adding all those up. I'd be interested to see our average points per game over the past couple of years. Probably be immense. We've had some pretty stout offensive output. Of course, defense is what wins games, but our offense is definitely impressive. This is not a great question, so we'll skip this one. It's formatted in a weird way. You have to find the answers along the diagonal. And I don't like it too much. So identity matrix, page 378, talks about what I've already showed you, and they've got this general, so I gave you a specific example of a 3 by 3. They've got this more general example of size n by n. So it could be any square matrix. 1's on the main diagonal, 0's everywhere else. And if I multiply a matrix of like dimension to it, I always get that same matrix as a result. And it's like multiplying by 1. It's an analog to that in the matrix multiplication world. Okay, so let's solve a system of linear equations. So when they say Gauss-Jordan elimination, they just mean those row operations we already talked about. So first thing we need to do is convert this to an augmented coefficient matrix. So we're going to use RREF. Do all this at once. And I told you saw me do it by hand. You don't need to see that again. We'll use the calculator from this point forward. But tell me what these elements should be, Ashton, on the first row here.
2, 2, 3, 3.
Excellent. What about the second row, Logan? Yeah, you guys got this. I won't patronize you. And the variables are named weird, you know, x1, x2, x3, but there's still 3 separate variables, so don't let that throw you. So we plug this into the RREF machine, which does all those row operations for us, and the result's going to look like this. And whatever's here is x of 1, x of 2, and x of 3, respectively. So let's do that. Go to your matrix, edit A, make it a 3 by 4, which it already is here. So 2, 2, 3, 3, 1, 3, 2, 5, 3, 1, 1, 4. Double checking myself here. Uh-oh. Yeah, that's right. 2, 3, 1. Then 2, 1, 3. Okay. So go to Matrix, Math tab, navigate up or down to option B, RREF, then call matrix A as the argument. You get this, so we see that x of 1 equals 1, x of 2 equals 2, and x of 3 equals negative 1. So 1, 2, negative 1. So x of 1, x of 2, x3 equals okay, that's a pretty essential skill. You really need to be able to do that. So that's your default for solving systems. And in general, ladies and gentlemen, I don't like to muddy the intellectual waters with multiple ways of doing the same thing. So I don't do a lot of redundancy. However, in this chapter, I will do a couple of redundant things. I'll show you other ways to do this exact same thing, specifically matrix equation way and the Cramer's rule way. The reason why I do that is because I have seen ACT questions that specifically target those exact skills. In other words, they'll say, apply Cramer's rule to this system and show me what step 2 would look like. And so there's no way to answer that question without an understanding of Cramer's rule. So even though it's a redundancy, I'm going to go through a couple other ways by the end of this chapter to do this same thing. However, like me, I think this should be your default way because it's just the easiest and most convenient from my point of view. Okay, so now let's do a matrix equation way. So the matrix equation way. So matrix equations, first of all, we're going to define A. A is our coefficient matrix, not augmented with the solution. So we're just worried about the coefficients of our variables. And then B is that solution column over here. And then X is just a list of our variables in a single column, like so. So once you have those three defined, a little bit of matrix algebra, which is slightly different than regular algebra. I know that A times X equals B. That's just from the original system. Now, if I multiply on the left by the inverse of A, I get this. I have to do it to both sides, of course. That's legal. So if I multiply on the left over here, I have to multiply on the left over here because there's no commutative property. Can't just put them both on the outside, for example. Now, what happens is these cancel each other out, and I get X equals A inverse times B. So this accomplishes the exact same task as RREF. So if I take A's inverse and multiply that by B, that's going to give me the solutions. So let's define A in our calculator here. We want it to be a 3 by 3 this time. It is 2, negative 1, 1, 1, 1, negative 1, 1, negative 2, and then 1. Checking myself. That's right. Now I need to define B. So B is 3 rows by 1 column. Not what I intended to do. Three by 1. It is negative 1, negative 2, negative 2. Now I need to do A inverse times B. So I call matrix A, and then I hit the inverse button. Do not use caret and then negative 1 in parentheses. That will throw an error. So use the inverse button on your calculator to find the inverse of a matrix. So A inverse times B. Let me take a look. And that gives us an answer. Oh, you found it? Okay. So negative 1, 2, 3 is our answer. There's another way to do the same thing that we did with RREF. Another way to solve a system. Sorry.
Can you pull a guide for that calculator?
Sure. As always, stop me if you have a calculator issue, confusion, problems of any kind. Okay. No questions. So inverse of a square matrix. The inverse, to prove inverseness, it must be the case that if I multiply those two together, the result is the identity matrix of the same dimension. So if I think two matrices are inverses, I can test that by multiplying them together and seeing if I get the identity. So this is a way to test for inverseness. Not an easy word to say. So let's see if these two are inverses, shall we? Multiply them together, and I could probably do this by hand just about as quick as I could do it in the calculator. So this is the case where not a whole lot of time is saved. So I have 5 times 5 is 25, 6 times negative 4 is negative 24. 25 plus a negative 24 is 1. The second, first row, second column, 5 times negative 6 is negative 30. 6 times 5 is 30. Those sum to 0. Second row, first column, 4 times 5 is 20. 5 times negative 4 is negative 20. Sum to 0. 4 times negative 6 is negative 24. 5 times 5 is 25, which sum to 1. So are these inverses?
Yes.
Indeed. We have the identity matrix as their product. And so they are indeed inverses. So our answer is yes. Emphatic. Not quite all caps emphatic, but getting there. Questions? Okay, proving inverseness. So finding the inverse. So to find the inverse, you could of course use a calculator, but instead I would need a formula. So the formula is A inverse. If I let A equal A, B, C, D. So its elements are like so. Then I have 1 over the determinant of A times this scrambled up matrix. Like so. So that's the formula for finding the inverse. And it also has to be the case that the determinant must be non-zero. You heard me say that earlier, but here's why. Because in the formula, if it's 0, you get division by 0. And this absolute value sign plays a double duty here. So it means absolute value for a number, which is distance from 0. But for a matrix, it means determinant, which is not really related to absolute value in any specific way. But if you have a matrix as your argument, those double vertical lines mean determinant, something to make a mental note of. It can be confusing if you allow it, because it's also used for the absolute value. Okay, so let's plug in our specific values in here. And see if this exists. So first of all, the determinant of A, which I could also write as this. So that's A times D minus B times C. So in this case, that's negative 4 times negative 5 minus, questions?
I don't understand what you're doing there.
So this is the formula for the determinant itself. And this is the formula for the inverse, which depends on the determinant. So we got to find the determinant first. So this is the formula to find the determinant. This is the formula to find the inverse. We've got to plug this value into our inverse formula. And it has to be non-zero for the inverse to even exist. So we need to find the determinant first. And that is A times D minus B times C. In a 2 by 2, it's different for different sizes. So that doesn't hold in general. If it's a 3 by 3, this formula is different. If it's a 4 by 4, even another formula, and so on. So only for 2 by 2s is this valid. This is a 2 by 2, so this is valid. And then that's minus 6 times 3. Or some people write it C times B, doesn't matter. The same thing. So that is 20 minus 18 or 2. So my determinant is 2, and that gets plugged in here for the formula. So A inverse, and it's also non-zero. So that tells me that the matrix exists. So this is D, so that's -5. A down here, that's -4. And then these just change signs. Flip those. Change the sign like this. Okay. So when I multiply everything by 1/2, you get this. So we use the calculator to check ourselves. Matrix, edit. We're going to edit A, make it a 2 by 2. And make it -4, 6, 3, -5. And then if I quit to the home screen, call matrix A, and then use the inverse button. Hit this, now I have to hit math, enter to convert that to fractions. You see we have the same answer. So that's finding the inverse of a matrix by hand, and then you can also do it by calculator, but you do know how to do it by hand if you had to. If I had a gun to your head and said, convert this matrix into its inverse, you can do it. With or without your TI calculator. Question. You just stretch it? Okay, that's cool. Questions, anybody? Okay, so far, you should be able to multiply a matrix both by hand and by a calculator. You should be able to determine if two matrices are inverses. And you should be able to find an inverse if one exists. So are all those things true? It's good to keep a running tally in your mind of what we've covered. All right, so sometimes they're not true. I'm assuming that might be the case here. Let's see if we can find this determinant real quick and just see if so sometimes it's written like this, sometimes it's written like this. It means the same thing. So it's AD, so that's 36 minus 4 times -9. So it's non-zero, isn't it? Yeah, so that one does have one. We can find it real quick with the calculator. I was hoping this would be singular so I could show you what that looks like. But we'll run into one eventually. That was a mess, isn't it? So, yeah, it does exist. This is it. It's not singular. That one's not either. Bummer. So finding the inverse, what I just showed you is one way to find the inverse. Now, I don't like to muddy the intellectual waters, but here's another way to find the inverse. It's by augmenting the identity and row reducing. It can be done very quick by calculator as well. This is what we just talked about on page 381. That slide really should have came before the example, but whatever. Try to make a mental note to go back and fix that later. Okay, so find the inverse of a matrix if it exists. So let me use the other method for this one. We can use the determinant to see if it exists. So this is 40. Ooh, we got a problem here. So if I find the determinant, remember that's this, so that's 40 minus 40 equals 0. Finally, we found what we were looking for. One that doesn't have an inverse. And I wanted to show you what the calculator says when you try to find it by calculator. -5, 10, 4, -8. So if I say find the inverse of that, it will tell me singular. So that singular means no inverse exists. Exactly. This one will do the augmented identity way to find the inverse. So you just, over here, you augment the corresponding identity matrix, and then you RREF that funky matrix, and you're going to get this, or whatever is here, is the inverse of that original matrix. This is another way to do what I did before. Again, don't like muddying intellectual waters, but in this chapter, not necessary. So let's find its inverse using this method. So I need to define matrix A as a 2 by 4. And it needs to be 0, -2, 1, 0, 1, 3, 0, 1. And then I need to RREF that bad boy. So matrix math, navigate to RREF, which is B as in Bravo. Call that matrix A. So it's 3/2, 1, and then -1/2 and 0, I believe. Yep. So here is our inverse by that technique. All right. So still, we know the same amount of things, but we know more ways to do those things. We know how to solve a system using both a RREF method and then also by the matrix equation method using inverses. We know how to find an inverse using the formula that included the determinant, and then also by this augmented identity method. Determinant of a 3 by 3 matrix, this will be done exclusively by calculator. There's just too many ways to screw this up. It's about 40 individual calculations or something like that. No need to do this. It goes beyond the scope of pre-calculus. So we'll just use a calculator for this. There is a by-hand method. Know that it exists, and if you're a math major, you'll have to use it in the class Linear Algebra sophomore year. I had Linda Lawson, I believe was her name. She was the meanest teacher ever. But if you went up to her desk after class, she was the sweetest old grandma. So she was bipolar or something. I don't know. Okay, so let's find the determinant of a 3 by 3 matrix. So we'll define A, actually it says D, so we'll just call it D. And it's going to be a 3 by 3, and it's 3, 1, 0, -2, -1, 4, and then 1, 2, 5. And so matrix math determinant is the first option. And then we feed our matrix into it, D this time as in delta. And it tells me that is -25. And so does the inverse exist? Yeah, because it's not 0. And it is square. So we'll find its inverse by calling that matrix. And then using the inverse button. Oh. So that's, well, take too long to write, but you see it there. Don't waste a lot of time with tedious transcription. You guys should be able to find that pretty easily. So the inverse exists, easily found by calculator once we confirm its existence. That's it for chapter 6, part 2. Your assignment shall be page 383, numbers 3, 4, 5, 9, 12, and 13. Email me if you've got anything you're confused about. There'll be no meeting tomorrow because I'm taking the day off and I've got some things I got to take care of. But feel free to email me with any specific questions. Oops, accidentally started the jam. You don't want to just